Okay, shall we get going? So this week is on interpreting regressions, multivariate regressions, revisiting some of the concepts that we looked at last week, but in more detail. I guess more complicated, but the basic principles and ideas remain the same. So this is the plan. We're going to go back to what we started first week on, which was looking at causality. And we're going to go on to talking about multivariate regressions, which are very similar to the regressions we were looking at last week. Regression output table is more of a kind of a practical, something of more practical use of how to interpret regression output tables and coefficients in a regression model. Okay, great. So last week we looked at things like this. So we began with an idea in our head as to what the world looked like. We wrote it down, a model of it. We got some data, we fit the data to the model, and we ran the regressions, and we came up with estimates for alpha and beta. We also talked about what the interpretation of these coefficients is in this simple setting, and then we talked about standard errors, measures of the variance in the data, and how we need to take that into account when we're looking at beta. And also we looked at the R squared, so that the measure of how much of the dependent variable can be explained by the independent variable. So one of the first questions for this time is beta in this regression causal? Can we attach a causal interpretation to it? And what that means is that if it is a higher weight of the mother causing the weight of the offsprings we have, or is it in fact just a correlation? And I'm sure you've met the difference between causation and correlation before, and why correlation does not imply causation. And so we're just going to quickly kind of look at that as well. So imagine that you have a perfect model, a perfect representation of what the world looks like. And just to kind of, as an underlying thing, we're assuming that the world reacts in a linear way, i.e. we have something plus something else plus something else plus something else. That's just a blanket assumption, rather than we have more complicated ways of doing things, but it doesn't really matter. The intuition is the same. So imagine there exists a perfect model. We're modeling income, because we're economists and we like income, we like numbers, and we have all of the variables that we think could possibly influence income. So I've got ... here, it goes on forever with all of the things that we think could influence income. If we had such a thing, and we were 100% sure, that in this model we had every single variable that could impact income, then we could attach a causal interpretation to each of them. Because there's nothing else that could be confounding us, that could be in the way. But there are two issues with this. Firstly, and most obviously, we don't know what a perfect model for income is. We can think, okay, income is probably related to your years of schooling, probably related to how much experience you've had in the field, probably related to your ability, it's probably also related to what field you're working in, etc., etc. But it's not possible for us to think of everything. But kind of maybe less obviously, there are some things we can think of that we're pretty sure impact income, have an effect on income, such as ability, that we can't necessarily measure. So how would you measure someone's ability, someone's intelligence? You could give them an IQ test, but is that a perfect measure of intelligence? Probably not. You could maybe look at their year 6 SAT scores, that's also not going to be very useful. There's no steadfast way to measure this, although we're pretty sure it is going to have an influence. So that's going to be an issue. So we have two issues with this kind of perfect model. But what were we looking at before, and what is the difference? And by the way, this is a multivariate regression, because we have multiple variables, but we'll come to that. So the issue before is that we just had two variables. In the bivariate case, we're looking at weight of mother and weight of offspring. Now it could be that we see a relationship between them and it's a very strong relationship by all the metrics we had previously, but it might not make sense to us. So, for example, on this axis is the number of murders in the US, and on this axis is the market share of Internet Explorer. So there's a strong correlation between both of these. They're both decreasing. And we can plot these on a scatter diagram like we had before, run a regression, find the line, and we can be pretty confident that there is a strong relationship between them. And so statistically speaking, we have a good regression here. But if we actually stop and think for a moment, we realize that claiming that more murders in the US causes Internet Explorer's market share to decrease, or oppositely, is not a very sensible statement. And this is where the disciplines of statistics and economics diverge. So if you're a statistician, you see data points, and you do the regression, you plot the line, and you think, fantastic, this is a great regression. If you're an economist, you stop to think a moment what the actual underlying model that you're doing, or maybe not an economist if you're or anything, and maybe obviously some statisticians as well. You stop for a moment and think about what is actually happening and realize that although you've plotted this regression and you found this relationship, it might not actually make any sense. And it's very important that you do this and that you do think about what is happening, because right at the beginning of last week, we looked at two cases where regression analysis has had a really big impact and where they've drawn very strong and important inferences. One where they showed that the US justice system was institutionally racist, and the other, in the 80s anyway, not necessarily now, and the other where Galton, you're nodding your head at the institution of racism.
Definitely still now.
Okay, I wasn't going to make that claim. And the other where Galton showed using his P's what he considered to be support for eugenics. So it's very important that we have the right interpretation. But this regression, just to reiterate, by the metrics that we looked at last week, which was the coefficient estimate, the measure of variability, of variance in the data, in the standard error, and the R squared, by all of those metrics, this regression is really good. We have a coefficient not equal to 0, we have low standard errors, low variance, and we have a high R squared. But if we're just thinking outside of the statistics, we don't think this is a good idea. So what's going wrong here? What's making us, the statistics say there is a relationship, but us say there's not? And to kind of demonstrate this, we'll go for a simpler example, which is a classic, really. This is a relationship between the consumption of ice cream and the deaths by drowning. So this implies that as the consumption of ice cream is increasing, more people are dying by drowning. So we imply from this that the government should put a large tax on ice cream, because that way we're going to decrease the consumption of ice cream and decrease deaths by drowning. Great. But what do we think is going wrong here? We think that there's some variable that we haven't included in our model, in our regression. This is just a bivariate regression again with two things. And we think that this variable has an effect both on ice cream consumption and on the deaths by drowning. And that once we take that into account, we might find there's no effect other than that of ice cream consumption on deaths by drowning. So in this example, it might jump out straight away, or after thinking about it for a little bit, after thinking about how the world works, that temperature has both an effect on ice cream consumption and on deaths by drowning. As the days get warmer, we'd expect the amount of ice cream you consume to rise. But as the days get warmer, we also expect people to go out swimming more. and therefore to die of drowning more. So perhaps what's driving this relationship is a third variable that we haven't taken into account, being temperature. Now, in this example, I said it was simpler because that comes quite quickly to mind. Because of the way that we think about the world, just by having lived in it, we can see this relationship quite quickly. However, you might not be able to come up with an explanation, a third variable that's driving both of these. I don't know if anyone has any ideas as to what might be, what is correlated with Internet Explorer market share decreasing and with murders in the US decreasing.
I have a causal link. That Internet Explorer is so terrible that you get frustrated in other people.
Yeah, see, I thought maybe it was murderers in the US, they were the only people who used Internet Explorer. And because the murder rate is decreasing, we assume that the number of murderers is decreasing. And therefore the market share of Internet Explorer is decreasing. And these are ridiculous kind of explanations because they don't fit in with how we think the world actually works. So this is a harder example because we don't know exactly, we can't think of one variable that does both. It's probably the case that if you simply included time, years in your regression, 2006, 2007, 2008, 2009, 2010, 2011, most of this relationship would disappear. I mean, just saying that time is perhaps not that useful, it's probably something similar to social norms and more kind of less precise concepts. But that's why this is a better example to think about. So we think that there's some other variable, and we can kind of visualize this in this way. So we think that hot weather causes higher ice cream sales, because people eat ice cream when it's warm. And we think that the weather getting hotter causes more deaths by drowning, because we think more people go swimming and therefore more people will succumb. So when we're just using these two things in our regression, we're seeing this arrow, ice cream sales, deaths by drowning. But in fact, what's happening is there's this third variable that does both. So we think that the impact of ice cream sales, once we've taken out the fact that ice cream sales is highly correlated with hot weather, the impact of ice cream sales on death by drowning will be low. That's our hypothesis. That's what we think the real world works, how we think the real world works. So the question is, how does this work in a regression setting, in a more kind of concrete manner? So this is our first regression model that we have. We think that death by drowning is some constant plus beta times ice cream sales plus some error. So this is exactly what we had last week. And when we ran this on the data, we got some data, we got this. So death by drowning is some constant at 0.3 times ice cream sales. So this means if ice cream sales increase by 100, the number of deaths by drowning is going to increase by 0.3 times 100. So 30. Yes. And as I said before, the standard error, the measure of variability in this is low. It's less than 2 times the coefficient, which is our rule of thumb for saying that it is different from 0. We're confident of that. And the R-square is high, it's about 70%. So then we think a bit more and we realize that we're just blindly following the data here, and maybe there's an explanation for this. And that is that temperature has a role. So as temperature increases, we think that this is affected by both of these things. So a difficult question, but one that I think is definitely worth thinking about before I just tell you, is what do you think is going to be the effect of putting this term into this model like we've done here on the coefficient of beta. On the coefficient of beta, on the standard errors of beta, and on the R squared. So, take them one at a time. What do people think is going to be the effect on the standard error of beta? That is the measure of variability in this independent variable, ice cream cells. And this is a difficult question, but it's at least worth thinking about, I think. If we've included this third variable, what's the effect on the standard error? Man, that's not allowed to answer. I don't know if anyone has any clues? Just a random guess? Can it go up, down?
Yeah, I think it would go up.
You've got a 33% chance.
I think the variability would go up.
You think the variability would go up?
Yeah.
Okay. Why?
Because if you're introducing if you're introducing error, maybe the range of possibilities increases. I don't know.
Okay, fair enough. Anyone got any contradictory or the same intuition? Or no intuition too? Okay, so that's the standard error, and I think we'll go through all three of them in the grand reveal. So, what do people think is likely to happen to the coefficient, to beta itself? So we're expecting that all of the relationship between this and this is actually explained by temperature. So what do we think is going to happen to the coefficient? And this is probably more clear-cut than the... Not that it's easier, but it's more... Anyway, I mean, just thinking about it is fine. That's the point. So, if it were the case that our third variable, temperature, explained most of the reason why ice cream cells affected death by drowning, then once we've included it, if the beta coefficient didn't decrease, then our hypothesis is probably wrong. So we expect that a lot of the reason why ice cream cells affect death by drowning is because ice cream cells is correlated to temperature. And so a lot of the reason why this beta, which represents the relationship between these two, is greater than 0 and we're confident it's greater than 0, i.e. standard error is low, is because of the unobserved variable temperature in this regression. So once we've included temperature, we'd expect beta to reduce, to come closer to 0. Yeah.
How would the maths know from this formula that, I mean, all these three variables are correlated with each other. I mean,
right,
even
yeah.
though there's no causal relationship between ice cream cells and death by drowning, they are correlated. So how would this formula figure out which of these is actually the causal factor and know that, or like how would that make beta decrease? Because the formula can equally assume that ice cream cells is the causal factor and temperature is just a...
That's a good question. And we'll have to go a bit further, but I think it's worth it. So we've got an equation. Our dependent variable y equals, we'll just ignore the constant for a time to really care. And x, which in our case is ice cream cells, add either to z plus some error. So, and z is our temperature. So, before we had this, we can think of, we can think of including z as conditioning on the variable z. Now, what does conditioning mean? It means we remove the correlation or the effect that z is having on x. So once we've included both of these, what these coefficients are going to give us is the effect that x is having on y removing z. And this coefficient is going to give us the effect that z is having on I removing x. So we think that, so we think that x is correlated with, we think that x is correlated with z. Or we think that most of the reason why x has a relationship with y is because of z. So adding z here is equivalent to saying, what is the relationship x has on y removing the effect of z? And similarly, if we just had this, it's what is the effect that z has on y, and then we include this term, and it's what is the effect that z has on y removing x. But we think that if this is temperature and this is, it was ice cream, I'll go for like temperature, then we think that ice cream, that the effect of temperature on drowning is not going to be affected much by ice cream. So including or not including this variable shouldn't make much change to this. But we think that temperature does have a lot of effect on drowning, and the ice cream has a lot of effect on temperature. So including this variable or not will have a big effect on this.
But what if they're all perfectly correlated? With each degree that it gets warmer, there's one more ice cream consumed and there's one more person drowning. If they're all...
If you're saying like if the data just looks like, this is death by drowning, this is ice cream sales, and this is temperature, then how does it like mechanically know?
Yeah.
So we're gonna have.
Or in that case, maybe it couldn't, and I don't understand how. Yeah. Could it in that case figure out which one is the causal, which one is the cause and which is the fundamental?
No.
Okay.
I don't think it could.
I just wanted to kind of point out is that the statistical tools can't tell you what's causal, and that's where scientific our theories come in. But what it can tell you is the proportion of the correlation y that's explained by x or z, right? So the example Luke was giving is that if you have this regression here, and we include ice cream, then what we're getting is that what's the impact, how much of y is correlated with ice cream given that we know z, given that we know temperature. And hence that would be significantly lower, and we'd find that really it's just temperature that's causing the correlation. But given, once we know that, that kind of fits in with our theory that it's actually temperature that's drowning. So I think that's where econometrics starts moving away from statistics, and that's that you bring in your theories to explain.
So we could, if we have, I'm just going to go down here. If we have two models, beta 21x and beta 22z and epsilon. So we have two models with three different betas. Then we can think of, although it's not kind of mathematically entirely correct, but we can think of beta 11 as being equal to the correlation between these two. That's one way we can think of it. It's not exactly correct, but it's one way we can think of it. And then in this case, beta 21 is equal to the correlation between x and y, given that we know what z is, given z, having taken into account z. And similarly, no. So we think that knowledge of z is going to have a large effect on this coefficient, on the coefficient of ice cream sales, knowledge of temperature. But we think that knowledge of ice cream sales is not going to have a large effect on what the correlation between temperature and death by drowning is. Does that make more sense? It's
a bit. Yes. I don't understand
No.
what it means in mathematical terms to have knowledge of that.
Yeah. Okay.
But I guess I.
So this is. Yeah, I don't really know how to do that.
I think initially actually in one of the lectures I thought I'd go over the concept of conditioning.
Yeah.
I think the example I'd come up with is kind of thinking of GDP, and so let's say you've got 3 variables that you can observe. I'll just kind of do it on the board so if people don't need. So if you're looking at, so this is just kind of giving you the concept of what given means, and then like more mechanical kind of what regression is saying. Is that when we talk about conditioning, that's I'm interested in the concept of like what explains GDP, right? And there's this famous paper by LSEUPR that argues that it's institutions that kind of explain what growth levels are in the economy. So then, let's say we have some sort of perfect measure for institutions. Actually, this is an endogeneity problem. That's what I don't want to get into. So that violates the huge problem with regressions.
Yeah.
Okay, let's go with the. Let's say I think technology is what explain. So we have GDP here, right? And then the thing is, there's a theory that it's actually the distance from the equator that explains what GDP is. And then you'd run a regression, and you'd kind of include beta 1 latitude. Is that the one from the equator? That's not known.
Yeah, latitude. Yeah, latitude.
Okay. Latitude. Plus some error. So by doing this, we kind of understand how much of the GDP varies with latitude. This is purely a correlation story, right? We generally find richer countries in the northern hemisphere, so we'll find a strong correlation here. Let's say that we could kind of, and someone argues it's not to do with that, it's more to do with the education level that the people in these countries have. And this is just kind of the ice cream, like this is just a random variable, it just happens to be a coincidence. And then when we factor in education, what GDP is then doing is that we now when we see when we look at this here, okay. So obviously there's a big correlation between education and GDP as well, right? But by including both of these here, we can capture the effect education has on GDP while controlling for latitude. So it's kind of like if you did a scientific experiment and we could ensure giving everyone the same latitude but different education levels, we can do that. So what this mathematically does is kind of start separating out the where the correlation is coming from. And like conditioning is kind of like a scientific experiment control. So it's the effect that education is having on GDP, given that we know the latitude of these countries.
So if we take like a latitude of I don't know what latitude is measured in, of 10, some number of latitude, and we look at the education levels of the countries at that latitude, then we compare those, and then so it's like we have the knowledge of latitude is informing our correlation or our interpretation.
So in this, while we see ice creams are correlated with drowning, and so is temperatures correlated with drowning. But by just looking at the impact temperature has, when we include everything in the regression, what we're looking at is the impact, the correlation of temperature with drowning, controlling for the fact these people might have been eating ice cream, kind of thing.
Yeah, and we don't know that the information of ice cream sales is going to give us much more, it's going to change many things there. But the other way around, I think that lots of things are going to change.
Yeah, I think it's quite a stupid question, but the way that we're describing conditioning seems to me a lot like how I've understood regression up until now, just in general, which is isolating one causal variable in a group of other variables that might not be significant. Could you help explain the difference there?
Yeah,
this
I
part of
mean,
regression?
I think it's not a bad way of thinking about it. How you think of regression in terms of Is that possible for you to articulate, or?
Yeah, I mean, just broadly speaking, it seems like a tool for identifying when you have a range of sort of noise, what noise is important and what noise isn't important. So what variable is causally linked, I guess, and what wouldn't be.
Or at least correlation.
Okay.
Yeah. Yeah, so when you... So you're saying if you have some kind of like... Those are poor crosses, but you have some kind of data in like a bivariate case, and you have, if you had GDP and sorry, it was saying institutions. It's probably okay. Yeah, we'll go with that. Then what? So regression run fits a line, and we're saying that that's you're removing the you have the error term, right? And so you're finding all of the variation in GDP that can be explained by institutions is the coefficient on institutions in this kind of and that would be beta, right? Is that what you mean? So if you had like GDP conditional on institutions, then you would just get this kind of error in kind of massive abuse of notation.
I can explain it visually, but I feel like it might lose people then. I don't know.
Shall we move on? I think that's a good point. And I'll think about it a bit more, and maybe next week we can revisit that. Once I've got my head together. Okay, so something slightly less high level. Look at some tables. So, and this is kind of intuitively or intellectually maybe less interesting, but practically much more useful. Anyway, being able to interpret coefficients and read regression tables. So this is the model that we ran, and if I go into Stata, which you don't know what Stata is, it's just like a software package for doing these kind of things, and I run this in Stata, I'll come up with something that looks a little bit like this. And this is probably what you may have seen in academic papers, if you've read any that have kind of empirical work in. So this is a regression table. We have our R squared here, the amount of variation in death by drowning that can be explained by ice cream sales. Here we have what the dependent variable is, the y variable is, death by drowning, and our two coefficients. This is what the coefficient of ice cream sales and the intercept. So I've kind of highlighted the two main important things: the coefficient of ice cream sales and the standard error of that coefficient. So we had the basic rule of thumb: if the standard error is less than 2 times the coefficient, then we're confident it's not equal to 0. And we can see that this is the case. 2 times this is 0.12-ish. This is 0.34. So we're confident it's not 0. But the stars give us a far more kind of more information about that. So 2 stars means it's significant at the 5% level. Now, significant at the 5% level means that, first of all, it means it's good news. Significance at the 5% level is good. 3 stars means significance at the 1% level, which is even better. 1 star means at the 10% level, and no star means at a higher level, and we don't care about that. Really, I mean, maybe we do, but we don't. So significance at the 5% level means that well, to understand that, we've got to go back to the beginning, right? So we have a population, we have a sample, we know what these words mean, and we've got a sample of the population, and that consists of data points for these 2 things. And then we ran our regression on it, and we come up with these estimates. If we got what we want to know is if I happen to take a different sample, is it likely that I get the same results, or is this just a fluke? So a 95% confidence interval means that if I took 100 samples of the data, I am 95% certain that this coefficient is greater than 0. If we were confident at the 1% level, if I took 100 samples of the data, I would expect 99 out of 100 of them, of these coefficients, to be greater than 0. So, in my opinion, what should really be reported here is something called the confidence interval. So the confidence interval is two numbers either side of this. Say, in this case, it might be 0.1 and 0.5. And this is the interval around this number that we are 95% sure, or whatever percent, this is 95% confidence interval, so this is the interval in which we're 95% sure this number lies. If we took loads of different samples, we would find in 95 out of 100 times our coefficient for ice cream sales would lie in this interval. Now this is perhaps more informative of this, but a thing to keep in mind is that it's not equally probable that our coefficient is 0.49. Because we have and we talked about distributions. If we, in a normal case, we have a distribution like this. So 95% of the values lie in here, and our mean, the value that we think is most likely is the one in the middle. So, it's probable that it's in this would be like 50% chance it's in this area, and 95% chance it's in the whole area. So that's what I mean when I say significance level. In general, 2 stars is standard, that's kind of the minimum requirement usually of claiming that a result is statistically significant. But 3 stars is even better, and if you have a paper that's based on something that's only got 1 star, then perhaps you need to kind of question it a bit, because what that means is that 1 in 10 times, or 10 in 100 times, if they took a different sample, they're not confident that that would be greater than 0.
So the stars are a measure of which margin of error was chosen? Sorry, can you explain are the stars correlated to a certain number that you choose as your margin of error?
Okay, so in using the confidence interval, I've chosen 95%. These tell us what percent we are sure, assuming that of it not being equal to 0. So forcing the beginning of the confidence interval to be 0, and the other one will just be symmetric. So this is kind of given the confidence interval, what is the percentage that we are sure that it lies within there, and this is chosen confidence interval, then what percentage do we have? So they're kind of the 2 sides of the same coin. So this is based on the standard error in comparison to the coefficient. And that's summarized here in the t statistic, which is just the coefficient divided by the standard error, 5.52. If the t statistic is larger than 1.96 or 2 or whatever, then we are confident at the 5% level that this is not equal to 0. Okay, so this is for the simple example. Now we have 2 tables for the simple model, the bivariate model, and for the model including temperature. So we thought that the coefficient would go down, and it has. You said that the standard error was likely to rise, and we got a bit sidetracked and I didn't get back to that. But So the standard error is the variability in beta, not in beta, sorry. Well, yes in beta, but it's a reflection of the variance in the ice cream sales data. So we expect that to not change. I mean, it's not a perfect world, so it's not exactly the same, but we expect that variability not to change very much. So we wouldn't expect the standard error to change very much, but we would expect the coefficient to decrease, and more importantly, that the ratio of these two, the t-value, to decrease massively. So this is much smaller now, and we can't be certain at no stars, so we think this is probably not different from 0. We think this is probably is 0. There's no slope coefficient, there's no relationship. On the other hand, temperature is highly significant. It has 3 stars. And it has a massive t-value. Even though its standard error is much larger, you've got to look at that in comparison to the coefficient. So we expected that. We expected this coefficient to fall. We didn't talk about R squared, and that is perhaps also not so clear cut. But we would expect that the temperature is going to tell us more about deaths by drowning than, or we'd expect, okay, so R squared is the amount of variance in our dependent variable that's explained by our independent variables. So now we have 2 independent variables, ice cream and temperature. So this is, we had ice cream before, so we expect the amount of variance that can be explained by both of these to be at least equal to the amount of variance that could be explained by just one of them, right? It's going to be greater than that. And so that's one of the reasons why this is greater. Although I've cheated a little bit here because what I've actually reported is something called the adjusted R squared. The adjusted R squared takes into account that if you just added variables to the side, you're always going to increase the R squared. Just because you're always increasing more things. You've got what you had before, but you've got more and more of them. So the adjusted R squared kind of deflates the R squared to take into account of this and to give you a more accurate representation. Okay, so that's higher, and I think that's probably actually a good point to end because we are over time now. So next week we'll go over that point about the conditioning. So then and we'll finish this, and then we'll look at a